All right, thank you very much for that introduction. I'm very glad to be here, and I'm going to be talking about cross-platform performance engineering with something called the Arm Allinea Studio. Before we get started, I want to point out that these slides are available here at this link. And first, I want to talk a little bit about what do I mean by cross-platform. So cross-platform in my mind means all types of architectures, all types of operating systems, a very rich and diverse ecosystem of HPC technologies. And ARM is no stranger to this kind of environment. In fact, for the past, I guess, 15 years or so, ARM's compilers have always been cross-compilers. The embedded stuff that ARM is best known for runs, of course, on the ARM architecture, but the compilers, the libraries, all the performance analysis and debugging tools that came with that were actually built for x86 workstations. So cross-platform coding and debugging is old news for ARM. What's new is that ARM is now gaining significant traction in the server space, and we're starting to see that rich ARM software ecosystem coming back to ARM servers. So, for example, we have setups like this where I took OpenFOAM and ran it on a cluster of ThunderX2 servers provided by HPE, and then sent the results of that simulation over VNC to a Windows-based tablet computer, which was also running an ARM-based CPU, a Snapdragon CPU. And so it was ARM on ARM. The whole thing was ARM architecture, but it was using the same software that you'd find in anywhere else on x86 or whatever. The point is, when I'm talking about cross-platform, it's almost as if the architecture doesn't matter anymore. ARM tools are designed to work on CPUs, GPUs of many different vendors. So it's really the whole purpose of using our toolkit is that you can move fairly easily between architectures and develop and debug across different architectures without having to think too much about what's out there. So that's cross-platform. How about performance analysis or performance engineering? So performance engineering is a structured method for improving the performance of your code. The idea is that we need to identify and resolve performance issues in the various aspects of the software application. And what I always recommend is that you identify hotspots in one aspect of the performance and then focus on that exclusively until you feel like performance has improved sufficiently that you can move on to the next one. So this is a typical workflow for performance engineering where you always begin by profiling the application. Don't assume that you just, that you wrote the code, you know how it performs. Don't assume that you know exactly where it's spending time. I cannot count the number of times I've sat down with scientists and engineers who, say that they know exactly where the time is being spent, and then a quick profile shows that no, in fact, the time was being spent elsewhere. And we'll even have a case study here where that came up in a very surprising way at scale in a GPU-enabled code. So I'll show you that in a minute. Start by profiling your code so you get a clear understanding of where time is being spent, and then focus on file I/O, communication, memory, compute, some aspect of your application, and try to identify how much performance gain is possible there. Now the orange numbers I've shown next to the various aspects, those are the types of slowdown I've observed in the real world when that aspect of the application is done poorly. For example, if you do file I/O in a bad way, you can easily see a 50 times performance degradation in your application. And it's a subtle difference from saying that, optimizing your file I/O will make your code 50x faster. That's not what I'm saying. I'm saying that if you take a naive approach, you may suffer severe performance degradation. So once you've identified your hotspots, focus on optimization on that hotspot until you're satisfied with the performance gains, and then go back and profile and keep doing it. Wash, rinse, repeat until you are satisfied with performance. Now the profiling piece, the orange box, that can be any number of tools, and there's a huge ecosystem of performance analysis tools out there. Tools like Tau, Scorpy, Scholastica, HPC Toolkit. There's a great many free tools. I'm going to be talking specifically about ARM's tools. The performance analysis and performance engineering tools that ARM provides commercially are bundled with a thing called the Arm Allinea Studio. So Arm Allinea Studio is one software toolkit that consists of cross-platform tools like Arm Forge and Arm Performance Reports. These cross-platform tools can execute, profile their work on x86, ARM, Power, NVIDIA GPUs, AMD GPUs. So they really are cross-platform in the sense that you'd expect. They even support Windows, Mac, and Linux to varying degrees. Bundled with the cross-platform tools in Arm Allinea Studio, you also have the ARM architecture tools, which are compilers and libraries specifically aimed at high-performance computing, and they execute on ARM architectures, generating code for ARM architectures. So this is the ARM on ARM part. I'll focus mainly on the cross-platform tools today. These are the ones that are mostly useful for you today. Most of the existing HPC systems are not ARM architectures. In fact, there's only one ARM system on the top 500 that is ARM based. But I hope more are coming. But we've got plenty of opportunity to use ARM software on x86 and Power-based HPC systems today. So that's where I'm going to spend most of my time. Now, typically the way you want to use these tools is over some sort of remote connection. So ARM comes with a remote client, ARM Forge comes with a remote client that will allow you to run a graphical user interface for the profiler and the debugger locally on your laptop, and then connect to the parallel job that's executing on the cluster backend. So I'm just going to demonstrate that right now using the cluster that we've got, our hands-on cluster. So normally I would SSH to a system. Let's grab. I'll say I'll be a student 15, unless somebody else has already picked it. Let me increase the size of that. I'll be student 15 on the cluster. Check who. All right, there's a couple other student 15s out there, so I'll pick a different one. Looks like student 3 is still available. All right. When you log into the cluster, you should have access to ARM Forge. The two commands are DDT and MAP. Now I can run these commands here locally, or if I want to run them through a graphical user interface, I can launch the Forge remote client. And the first thing I want to do is set up a new remote launch configuration. Go here and click on Add. I'm going to be student 3. And the remote installation directory is provided by looking at the path for DDT and MAP. In this case, it's opt-arm Forge 1905. Test that. That's working great. So at this point, I've created an SSH tunnel between the GUI, which you see on your screen here, and the head node for the compute cluster, which is located somewhere in Ireland. if I run or do anything from this GUI, those commands actually execute on the remote system. But as you can see, this GUI is very responsive because it's being rendered on the local system with the local GPU. So all the communication is done over an encrypted SSH tunnel, almost exactly as if I was typing commands directly on the terminal, but it's being done through a GUI, which is really quite nice. In fact, so let's get back to the slides here. So it looks a little bit like this. The client is running here on the local laptop, going over public network to a head node. When I launch a job on the compute nodes, the tunnel will extend down into the compute nodes, and it will feel as if I'm actually sat at a keyboard on a compute node, when in fact it's all remote and hidden away. This is much better than VNC or X11 forwarding. In fact, I did an experiment sometime last year where I was flying to Australia. So I was somewhere over the Pacific at well over 40,000 feet, going at 550 miles an hour, and I opened up this remote client and connected to the compute center in Perth and at Pawsey, and I was having just terrible network characteristics. Ping here is huge. Download speeds and upload speeds were really bad. But even with this level of network connection, I was able to use the GUI and run jobs in a fairly comfortable way. So you really don't need much to get off the ground with this GUI. It actually works pretty well, even under bad network connections. For reference, this is exactly how to download and install it, how to get set up with the remote configuration just as I showed you. And then you should see something that looks a little bit like this. So that'll give you access to ARM Forge. Forge is a combination of the DDT debugger and the map profiler, and it's already installed on the vast majority of the top 500 systems around the world. It supports ARM, it supports x86, it supports Power, it supports NVIDIA GPUs. The hardware performance counters available in these different technologies are all available in the same GUI. The profiles that come out of it are directly comparable, so it's nice if you're porting between architectures. You can make a nice apples to apples comparison of performance. And then
question.
Go ahead.
So it says, I remember that there may be a special trick to do double hop in connection. When you have a chance, would you please comment if this is true, and if yes, provide syntax for it? So if you had to go to ARM cluster, but through extra gate?
Yeah, sure. I'll show you that in just a sec.
Thank you.
So the last thing I wanted to say about Forge is that it scales out to huge numbers of processes. So you can have hundreds of thousands of MPI ranks, each executing, dozens of OpenMP threads, and Forge can cope with this scale quite well. So you don't have to worry about, extracting a mini app or isolating a kernel away from the main application. You can run your applications at scale and observe performance at scale. So the question was about Remote Connect if you have to basically go through a proxy. If you need to proxy through another system, under the remote connection options, there's this checkbox for proxying through a login node. That's one option. Another way you can do it is just string through through multiple gateways. So you would use the names of the hosts in the order you wish to connect to them as separated by spaces. So I might be, John at proxy 1 and then student 3 at something, for example. Now, which one you use, if you need to proxy through the login node or if you need to do a multi-hop, this depends a lot on your network configuration. I should also say that your local .ssh/config affects this because it really is just a wrapper around SSH. So if you have server configurations in there, for instance, I have one for Eisenbard, which is already, so I have an Eisenbard configuration, which I'll show you here. if I just say Isambard, I'm actually going to proxy through another system before I finally reach the Isambard. But this should work here to just provide Isambard, and it'll pick up the details that I've given it here in the SSH config. So this can get a little complicated, but if you have specific questions about your setup, I'll try to help you. All right, so what kind of things can you do with DDT? Well, you can take a look at individual MPI ranks to see where crashes happen. You can also track MPI messages. If there's, for example, a tag mismatch, you can watch MPI messages in flight to see if the sender and the receiver are matched up or not. You can drill down to the individual lines of source code to figure out exactly what's going on in those particular variables. And I'll demonstrate all of this interactively in a minute. Some of the more interesting features, you can do things like visualizing data structures. Oh, go ahead. Sorry, there's a question.
So just a comment from Ray. So basically on ALCF system, connection to the login node is basically enough, and we don't need to proxy through the mom node or ION on BGQ. So it's just a note. It is on the chat. Yeah, go ahead.
Good to know. So one of the interesting features here is that you can visualize data structures where if you get halfway through your simulation, you can pause the simulation and then do a 3D visualization of the data itself. This has actually been a very good way to diagnose correctness bugs where the code is not crashing, you are completing on time, but then the answer you get is wrong. You might visualize your data and discover, for example, in this case where I would expect, based on the problem, to have a nice sort of cup-shaped curve here, but instead I've got this weird zero line running down the middle. That can help me trace exactly how did that get written and how do I fix it. This works for multiple dimensions, so you specify the segment of the array or the dimensionality of the piece of data you want to model, and then you can draw that in 3D. And because the 3D is rendered on the local system with the remote client, you'll be using your local GPU, so it actually works pretty quick. Memory debugging also works. This varies a little bit from system to system. On BlueJean, for instance, you can't really do guard pages because improtect doesn't work. But most systems, if improtect is provided, then you can do guard pages. There are other checks like dynamic or binary instrumentation that will check reads and writes of certain addresses. You just use this slider to pick a value between fast all the way through thorough to determine what level of memory debugging you need. Of course, the more thorough you go, the more overhead you'll have. So try to stop, you pay for what you use, so try to stop where you get the answer you need without paying for too much. Covered this and this. Quick cheat sheet for the hands-on for future reference. Typically you do a module load for Forge or whatever the equivalent on your system might be. Compile your code with -G so you get debug symbols. I recommend using -O0 for the debugger. For profiling, you can do O-fast, O3, any kind of optimization you like, but do include the -G so that you still have those debug symbols. Then you can start either in interactive mode by putting the word DDT in front of your execution command, just DDT in front of the regular MPI run, or you can use DDT --connect, which will, instead of trying to launch the GUI on the compute node, will pause and wait for the remote client to connect to it. So I'll just demonstrate that right now.
John, while you're switching windows, I always get this one wrong. Do you have an ability of profiling applications that's already compiled?
Yes. Yeah, that's a good point. So ARM Forge does not require you to recompile your application at all. You can use any binary that you get. It doesn't have to be modified in any special way. The The profiling is actually done by periodically checking the program counter and taking those samples and comparing them against the debugging table. So as long as you have debug symbols in the executable, we should be able to see what's going on. The one exception is statically linked applications. If you are running on a Cray system, then you should relink your application so that the sampler code gets injected into your application binary. But on a dynamically linked application, you can use LD preload, or actually Forge uses LD preload to do that for you automatically. But in both cases, you don't have to recompile. In the worst case, you have to relink, but that's it. So I'm going to demonstrate using DDT in connect mode. If I have a simple application here that crashes, O1 simple crash, and I'll cat run script for you. So it's going to run the code. You'll see it crash. They're going to rebuild with debugging enabled and run DDT-connect in front of the same command. Oh, I should grab a few nodes here. Go and run. So compile, you'll notice I'm doing -G03, so this is fully optimized, no problem.
The -G will be required, right, to get any reasonable answer.
That's right. So first thing we see is we get a seg fault. We're not sure where. Now we're going to rebuild with debug offer. The only difference really between the two is that one of them is with 03 and the other's with 00 to make it a little easier to view. Now because I already had the remote client up and connected to the remote system, it's detected that a reverse connect request is coming through and it's asked if I want to accept this. So all I have to do is accept. At this point, the GUI will connect to the remote MPI system, or the remote MPI launch, I should say. Now, because I did that srun command, it's going to tunnel through the head node into the compute node where the MPI job is actually running. And it's picked up the command line. I'll go ahead and run. Connect. Oh, my apologies. I forgot I was playing around with UCX before I did this. Let me back it off to the stable config. Whoops, my mistake. This is just my fault. I decided to play with UCX and OpenSHMEM, and I managed to break my OpenMPI installation. Let me get one that I know works and try that again. There we go. I'm going to do DDT-connect. Okay, there we go. Sorry for the speed bump. All right, there we go. So at this point, I'm running over a tunnel. I can browse the source code. You can see that I can jump between different subroutines in the Fortran code. I can look at the application source all the way through the tree. If you have a complex application, this is really great for quickly navigating to different files. Fortran, C, C++, and Python are all supported, and you can mix all those together in any way and still run in DDT. And when it starts, when an MPI application starts, it always pauses at the first, well, right immediately after the call to MPI init. So from here, I can step through code. I can focus on a particular MPI rank. Ranks are shown here in this blue bar, 0 through 7. And I can insert breakpoints. Now, just to remind you, so when we first ran this, we went through a little bit of processing, and then we had a seg fault. So the easiest way to jump to the error in here will be just to run the code, wait for it to seg fault, and the debugger will intercept the problem. I'm going to click the play button, and almost immediately, seg fault, invalid permissions for mapped object. So let's hit the pause button, and it says that the seg fault occurred on this line. I wonder if there's a way I can make that a little larger to view. Sorry for the font size. So it's paused here on this line, and I can see the value of the variables on this line. For instance, I0, SZ, K, and then the values of the arrays A and B. So at this point, this is where I start to look at the code and think, now what would cause this to seg fault? If I take a look at I, okay, value for I is 0. A. Value for K is 5049. Here's SZ, which is 1024. And J, which is 0. So we have K times Z, 5049 times 1024, in an array of B. If I go look for the definition of B here, I see that B, it runs from, is a size times size, where size is 1024. So I've gone beyond the bounds of B by taking K of 5049 and multiplying that by 1024, because maximum value in B is 1024 times 1024. So why is K going so large? Well, here's the loop limits. And for some reason we have size times size here. That's a mistake. I'm pretty sure that this was supposed to be size times size. Now I can modify the code here. When I do these edits, the edits are again sent over SSH back to the remote system. So I can change the source, save it. Command V, I can provide a build command, which in this case I'm just going to say make all. Working directory. The same. Let's make clean all debug 1. Then we can restart the session. I'll hit play to run it again. So now we're running with the modified code that should have the correct limits on K. And it works. Bug found, bug fix. So this is obviously a toy problem, simple code, but the principle is there. You can see that I can pick an MPI rank, I can fix code, I can recompile it, I can do all of that from this nice user-friendly GUI with the commands executing somewhere on a compute node, some remote place, someplace. Now the hands-on exercise that I just went through exact step-by-step instructions for that are in the slides, and then you also have these cheat sheets if you need any more help. You can also run the debugger in offline mode. This is very useful for large, long-running jobs, especially memory leaks. If you have a memory leak somewhere in a massive application and it only seems to happen at scale after running for 2 weeks, then you could do a DDT -- offline, and that will tell the DDT debugger to basically sleep in the background until something goes wrong. When something goes wrong, print out a report of what the system state looked like at that point, and then exit. So along with DDT in Forge, you have Arm Map. Arm Map is a lightweight sampling-based profiler. It can show you what's going on in a sort of summary sense across multiple MPI ranks. So this one scales out very nicely, but it does have some caveats compared to other more detailed profilers. So Map, you can take it to hundreds of thousands of MPI ranks, each one of them executing many, many OpenMP threads. But to keep the profile size manageable, only the summary statistics of all those MPI ranks and threads is retained. So you can't select a particular MPI rank after the fact. When you launch your job, you can say, profile MPI rank number 5 and preserve that data. But in general, you can't profile all the MPI ranks and then zoom on anyone you want. Instead, it takes the trend data from every MPI rank, aggregates them all, and then provides that back to the GUI. And it's pretty easy to use. You do map -- profile on MPI run, and you get your profile. It will provide hardware performance counters, hotspot analysis, MPI information, IO information. You can get information about energy consumption if it's supported, things like IPMI or RAPL if you have an Intel platform. And it also works on multiple platforms again, so x86, Power, ARM, GPUs, and so on. Map looks a bit like, so Map is used with the same GUI. I'll close the debugging session. To profile an application, let's go for simple map profile. So in this case, it's just going to compile the code and then do map -- profile in front of an MPI run command. And then for good measure, I'm going to show how you can export the profile as a JSON file. That might be useful for uploading to a database. You can do this as part of a CI system, further processing in something like Jupyter Notebook, whatever you might want to do. I'll do map, connect. This -- connect flag is the secret sauce that connects it back to the GUI here. Without that, it'll try to launch the GUI on the compute node. Accept this command. Run it.
It's asking if it works with SRun as well.
Yes, you can use srun, kubesub, I think SGE, Slurm, Cobalt. What's the other one I'm missing? PBS Torque. Yeah, most of the common HPC schedulers are supported. So at this point, code is running. These red warning messages, you can ignore these for now. That's only because, kind of sidebar, the compute cluster that I'm using to do this hands-on demonstration is hosted on the AWS Graviton. So these are ARM cores in Amazon's EC2 cloud computing platform. The Graviton is not a fast CPU. It's designed for scale-out applications. It's not an HPC platform necessarily, but because it implements the ARM architecture, all the ARM software ecosystem works on it out of the box. Truthfully, this is, in fact, the first time I've done this demonstration on Graviton, and I'm completely confident that's going to work because it's just ARM again. There's no magic here. The only difference is in the performance characteristics. So some of the Graviton, some of the workloads you'll target on Graviton, things like Nginx, for instance, will run quite well. But if you had something like an HPC code, an NAMD or an OpenFOAM, for instance, be prepared to wait because it's not optimized for that. But it's still going to work. And so all the ARM tools like MAP and DDT work there as well. Okay, so we run a matrix multiplication kernel, and the first thing I get is a summary timeline of where time was spent in the code. Green is for compute, blue is for computation, and then brown is for file I/O. And I can also see memory usage. You'll notice that these bars, they have varying widths, and there's a dark line running through it at all points. So because it is averaging the performance characteristics over all the MPI ranks, what you're seeing is the statistical variation across of this quantity across the MPI ranks. So if I look, for instance, let me zoom in on a piece of the timeline. To do that, I just grab it, drag it, and then click on it. Makes it a little easier to see. The dark line in the middle is the average over all MPI ranks. Dark line below and above, those are the minimum and the maximum across all MPI ranks, respectively. It's not necessarily the same rank, it's just the minimum of all ranks at that particular sample. So you often get the case that different MPI ranks will be a minimum or a maximum over the lifetime of the program, but you won't be able to tell which is which in MAP. You just know that there was a minimum and a maximum. Now, typically, this kind of information is enough to identify any performance hotspots in the code. You really don't need the level of detail that you'll get, like down to the individual MPI rank, especially if you start to think about, it's kind of law of averages. If you have, maybe 100,000 MPI ranks, that's a realistic number for some applications. Then drilling into the one particular MPI rank to look at its performance characteristics, how much is it really going to be different from all the rest of them? It's more valuable to look for variations, outliers, things of statistical significance across all those data points, rather than looking at each individual data point when so many of them are more or less identical. So back to MAP. If I look at the whole application timeline, just up here I get a rough sense of where time was spent over the lifetime of the program. I can see that we started off with some communication, then we did some computation, then we wrapped up with some more communication, and then finally at the very tail end here we had some I/O. If I want to see line by line where time is spent, I can drill through the stack. This is showing me that 74.3% of the application's time was spent here in this mbolt function. If I drill into that, almost all of that time, of that 73%, 58.5% was spent here on this line doing basically math. Interestingly, 15.4% was spent on this for loop. And that actually tells me that Graviton is not doing a great job on branch prediction in this code. Normally, for example, on the Thunder X2, which has a very aggressive prefetcher and branch prediction engine, I see almost no time at all spent in this loop because it knows, exactly how many iterations to do, more or less. All the time is spent here. But on this particular platform, I'm seeing that this looping structure is expensive. That suggests it might be worthwhile to try to unroll this loop a little bit, increase the size of the loop body so that I don't have so many invocations of this branch instruction. Or I might try blocking to improve performance. Now, in the hands-on materials that I provided in the cluster, there's the same code that I'm showing here, but in multiple versions, starting with blocking and then loop unrolling and then other optimizations that facilitate auto vectorization with OpenMP. So you can see how each one of those optimizations will affect the performance on whatever system you have on hand. Another thing I can look at is hardware performance counters. I come over here to this menu and take a look at CPU instructions or do a preset of CPU instructions. This is going to show me the available PMUs. Now, not all the PMUs are available on all platforms. So on Graviton, I get cycles per instruction, I get total instructions, and I can see cache performance, L2 cache performance, and the branch predictor performance. But what I don't see are stalled cycles. For whatever reason, these counters are just not available on this platform. Now, if you go to another platform, you'll see a different set of availability. This is the same story for all performance tools out there. Anything that uses PAPI or perf, it has to deal with the data that's available. So this is what you'd get. There's MAP in a nutshell. From here, I can identify hotspots. I can zoom in on regions of interest, take a look at where my code seems to be spending time, and then come up with ideas on how to optimize that. And then back to that workflow I showed. After you make the changes to the code, recompile, run again, see if you had any gains. All right, so I'm going to close that profile and go back to the slides. Should mention Python profiling works. You can see line-by-line Python profiles. This is becoming more important in HPC because almost always the bulk of the compute time is spent in some compiled code wrapped under Python. But finding that particular piece of compiled code is sometimes difficult. So having a way to drill through the stack line by line all the way up through Python can be really useful. You can also do custom metrics. These are really fun because you can take really any quantity you could imagine and implement it as a custom metric. A custom metric mechanically is just a dynamic shared object that you would load alongside the map profiler. So any kind of C++ code you can write will get invoked every time the map sampler triggers. This means you could grab things like the error residual from your solver and show that alongside the power consumption of your core. You might see that you could actually watch your solution converge in the map GUI alongside the performance data for that application. And I'll have an example of that in a minute. Oh, here you go. So this is showing error terms from this Muscle 2 code, where we have an LU solver, and I can actually watch the error in the arrays dropping off over time as the LU step count increases. Generic cheat sheet. The last cross-platform tool I want to cover is performance reports. So DDT and MAP, they will get you down to the line level and you can see where time is being spent, but sometimes turning that information into action is tricky. You might not, easily, it may not be obvious that the path forward is to use blocking in your loop or unroll your loop or something like that. So what performance reports can do is analyze the data coming out of MAP and generate a report that says in plain English, your code is IO bound or your code is compute bound, and then make some suggestions about how you might address that. So in this case, for instance, we have a code that ran on an x86. We had 16 MPI processes with one OpenMPI thread, and I can see that most of the time was spent in MPI. So MPI, basically the code is compute bound. Now further down, I can see if the code is compute bound by collectives, by point to point. Let's see if I have a zoom. Yeah, okay. So I can look in the MPI block of the report to see if time spent in collective calls is excessively high, or if it was time spent in point to point. In this case, it's all collective calls. It's just not really a big surprise given most MPI codes. In the CPU, I can break that down between vector instructions and scalar instructions to know maybe my code is not vectorizing well. That becomes immediately obvious in the performance report. Perf report is very easy to use if you have a map profile. For instance, on this one, I have this map profile. To generate a performance report, I'd use perf report. Give it a format. Is it format? Forget if it's format or output. Output. Output results HTML. Give it the map file. The performance report will open up that profile, scan through it, and figure out what are the results here. In this case, it generates an HTML file that I can view in a browser. If you don't have a browser handy, you can also do results.txt. I know some people like to do this for continuous integration. To do performance regression, then have performance report generate a nice text summary of the performance and email it to them. So you can see, well, it's text. It looks a bit like this. You see how much time was spent. It says that this code is compute bound. This is how much time was spent in compute, in MPI, and then coming down further. L2 cache misses, mispredicted branch instructions. Cycles per instruction is low, which is good, but remember, this is Graviton. We don't actually measure retired operations, so that's not necessarily true. Thread code, total memory footprint. This can help give you an idea of how well your code is going to scale out. As you increase the number of MPI ranks, you can track what is the mean process memory usage, peak process memory usage. Make sure you fit into the compute node memory space. So I want to show a few examples of where these tools were used in the real world and actually were helpful. The first is a result that came from an Oak Ridge GPU hackathon at the Pawsey Supercomputing Center. And this was some work being done by this guy, Igor Bray. He was a head of physics and astronomy at Curtin University. And he has a code called CCC, which is a quantum mechanics code. And he's very familiar with the code. He's been running it for a long time. He understands it well, but the performance was less than what he would expect. So we took an initial profile of this code. It runs on the Cray supercomputer down there. So this is x86 with GPUs. And right away, we saw something really odd in the application activity timeline. So Igor understood this code. He knows that the structure is to do, in essence, do the same kernel 3 times. The first time you do it should be one, call it one iteration, and then the subsequent time should be n-1 iterations. So we would expect the first invocation of this kernel to be quite small, and then subsequent invocations to be quite large. But what we saw from the timeline in this big green blob is that the first invocation of that kernel, which should be 1 iteration, was taking as much time as the second invocation of the kernel, this last big green blob, which should have been n-1 iterations. So for some reason, it takes as much time to do this one kernel, 1 iteration, as it does to do many, many iterations. So we can see right away, okay, something weird is going on here. Another weird thing was that this code had a load balancer built in, where in the application diagnostics we can see the load balance. We expect, or Igor expected, something like a load balance of 90% or better. For whatever reason, we were getting load balances on the order of 80%, and this mathematically didn't make any sense. If you looked at how the code was written, and you looked at the maths behind it, we should have been getting at least 90%. So this was very strange to see. So we drilled in a little bit and we found that there was one line, this get channel info function, where that one line is taking something like 40% of the application runtime. That makes no sense whatsoever. If you look at the implementation of what that code was doing, it shouldn't have been taking 40%. So what was happening in there? Oops. Well,
Hey, John?
yes, go ahead.
So on the previous slide, it also has a line right below it that says less than 0.0. So why do you see it twice with different percentage?
Good point. So these are different invocations of the same function. Sorry, the chart is clipped off a little bit. But if you could see over on the right, you'd see the source line, source file and line number for each of these invocations. So the one I've highlighted is on a different line of code than the one below it.
Thanks.
Yeah. So if you were to take a function like printf, right, you'd have that thing all over the place. It's the same situation here. But we would expect this to be something like 5 or maybe 10%, certainly not 40%. What it turned out to be is that in this get channel info function, there was a Fortran array, and we had a loop over that array. Now, a loop should have been bounded by some upper limit. Essentially, if you wanted to go from 1 to n, where n was a parameter that was passed to get channel info. What happened was there was a typo where instead of taking that array from 1 to n, it was just the simple colon. So regardless of the size of the array, get channel info would iterate over the entirety of the array without and basically ignore the bound parameter that was being passed to the function. So all we had to do was change one line, change that colon from 1:n, and we limit the time that's spent in that function, all that useless work. And the results look a bit like this. So now if you look at the same application timeline up top, I think I can zoom in. Yes, here. Okay, so this compares the two, before and after. The initial profile showed that without imposing those limits, we were spending way too much time in the first invocation to get channel info. After fixing that bug, we get down to 5% like we'd expect, and the overall application time has been reduced enormously. Now this is running at scale. I really should have mentioned that at the start. You can't see it here, but this is on 192 compute nodes of the Cray supercomputer. So we're running, quite a lot of compute. There was an enormous amount of waste here. Igor was really, really excited to see that he had these kinds of savings because the numerics are the same, right? The final output of the code was the same. As a happy side effect, fixing this also fixed the load balancer. Essentially, because the code was doing a lot of operations that weren't being factored into the load balance calculation, once we were able to remove those operations so that the model matched what was actually being executed, we saw that the load balancer was working exactly as we'd expect. Now, unfortunately, I'm down to 2 minutes, so I'm going to skip over my other real-world application. I'm just going to summarize to say that MAP is very good at detecting I/O load imbalance as well. You can do things like detecting where I/O hotspots have occurred in the code. In this case, it turned out that opening a file was very expensive, so opening an intermediate file in something like dev.shmem was the right answer. You can also use MAP custom metrics to do detailed investigations of I/O. Here's an example from iPic3D where we had this large scale implicit particle in cell code with C++ and MPI, and we use a custom metric to instrument not only the application code but also the Lustre file server. And this allowed us to match the performance characteristics of the application to the operations occurring on the Lustre metadata server. So we could see where a large number of file opens or a higher Lustre read rate would be overlapped by computation on the compute node. We could also see spikes corresponding to checkpoint writes, things like that. This custom metric has been so useful that it's been made public. It's out on the web in Arm's GitHub right now. Unfortunately, I'm out of time. Arm does make compilers, but I'm not going to talk about them. We also make compute libraries that are quite fast.
Thank you, John. We actually have a question from Lena. She asked if you tried running MAP on 2K to 5K nodes. Does it still scale?
Yes, so I've personally run MAP at up to 40,000 nodes. The record right now is I think 114,000 nodes. I'm pretty sure that's the record.
Okay.
That is impressive.
So if anybody's coming to ISC in Frankfurt next month, I'll be giving a tutorial and 2 workshops. All of this will be focused around SVE and performance optimization for vectorization using these materials here. Materials I cover today are compiler and Forge. You're welcome to SCP these to any system. All this stuff is public and free, so help yourself. I'll summarize there and see if there are any further questions. Thanks.